So if you look at the title of the presentation, just to clarify, I'm not going to talk about how 5G will evolve to 6G, for instance. So basically just to use this kind of case study to illustrate in general how future networks should be driven by different factors. Let's do. Our vision, basically 5G is a combination of different technologies and visions, including automation and the capability to transform data into knowledge, intelligence, and also make the boundary more blurred between the virtual and real realities. Okay, just a few words about the 5G Innovation Center, which was established in 2012, and that is the very first 5G-oriented research initiative in the world. As you can see, we have a lot of industry partners to support our work, including Huawei and all the mobile operators in the UK. Okay, so basically, in addition to the different wireless technologies for which I'm not going to talk about here, so mainly just two pieces of, let's say, contributions we would like to highlight. The first is the development of the 5G core network architecture, which we call flat distributed cloud. Basically, up to now, it is able to enable automated network slicing within 2 minutes. And also, we have developed our own protocol, which is called metadata protocol, which enables the transmission of user contacts from mobile devices to the network edge in order to, let's say, enable some intelligent network operations like predicting user mobility patterns, etc., in order to make the network operation more efficient. Okay, we also developed some network edge intelligence based on mobile edge or multi-access edge computing technology. So the main purpose is just to defeat the current limitation of the traditional TCP or even QUIC protocol to enable seamless delivery of 4K or 4K plus video across the whole internet, involving both the wireless access part as well as the public internet backhaul. Okay, so we have been able to achieve both the delivery of video on-demand content delivery as well as live streaming at the same time. So this kind of intelligence embedded at the network edge has already been wrapped into a specific network slice to enable, for instance, EMBB type services within a mobile environment. Okay, so talking about general, let's say, driving force, what made us think about designing something new for 5G at that time? Okay, so intuitively you can think about a lot of, let's say, reasons why we should do that, including, for instance, definitely there will be new applications which cannot be automatically supported by the legacy system, and also noticing significant limitations in 4G, and also the advent of new technologies, especially like SDN and NFV, which allows us to do something differently. Okay, but last but not least, probably you talk about, for instance, several years, we can move on to the next G. Okay, but that's not something technical anyway. So let me give you some example. Okay, so at that time, 2012, what made us think about the new requirements? So during 2011 and 2012 period of time, we were involved in a European project which aims to, let's say, enable seamless support of what we call real-time state estimation in a smart grid network environment. So the mission is to use some, let's say, access network technologies to enable these very stringent end-to-end delivery technology to support different smart grid operations. But we'll try different, let's say, techniques, including 4G, which is the most popular at that time. So unfortunately, if you look at the capability of a 4G radio, basically that's what the result we have got. It's definitely not capable of supporting such stringent end-to-end latency requirements. So definitely we need to do something in order to enable such kind of existing, let's say, operations. The second is from the core network side, basically we notice the signaling efficiency. Upon every user mobility event, the signaling has to be sent back to the mobile core, which makes the mobile core very heavily loaded with different sort of, let's say, signaling for different events. And then we thought about breaking down or collapse the current, let's say, mobile architecture in order to enforce some local handling of different events. So basically, such kind of principle has already been adopted by today's, let's say, 5G core network architecture, where you can have some local edge-based control and local breakout in order to efficiently handle such kind of user mobility dynamicity. Okay, now coming back to 2018, so we come to a new era. So basically, in this talk, I mainly talk about applications and services that cannot be supported. Okay, so in addition to other factors. So generally, the vision is now people start to talk about, let's say, holograms, holographic-based applications. So at this moment, basically, the main focus has been on the audio and visual purpose. But generally speaking, if we want to move ahead, we also need to talk about other senses like touch, which is a very interesting topic, linking to tactile internet, and also smell and taste. Okay, so intuitively, we need to better understand what are the key, let's say, requirements to support these additional senses in a more immersive way. So talking about specific technologies to support this kind of digitized sense, especially, let's say, smell and taste, to our best knowledge, and actually helped from Huawei Richard Lee's team. So basically, we have some preliminary understanding about how such kind of senses could be digitized and what are their basic requirements for transmission. Okay, and then talking about interactive applications, that imposes much more challenge, because basically everyone understands the requirement of modem to photon requirement, which is about 20 milliseconds. But if you talk about interactive applications, basically that's another level of let's say difficulty or challenge to be handled. Okay. Now, basically, what is the data rate, or let's say bandwidth requirements? So at this moment, we are more or less understand or get familiar to the basic requirement of 4K, conventional 4K or 8K video, which is about probably, for 4K, we are talking about probably a minimum, I would say, 10 megabits per second or up to 30 megabits per second. 8K might be more. And then moving on to 3 degrees of freedom and even up to 6 degrees of freedom, then basically the vision has been, the vision on the data requirements will be much higher, but these also largely depending on the capability of coding techniques. So intuitively you can see the mission of communication networks is just to increase the bar to support higher and higher bandwidth data rates. But from the multimedia or information processing point of view, basically they are trying to bring down such kind of requirements. So, but there is always a trade-off between the two technologies. So currently, 5G is here. Okay. So generally, the general vision is the user experience data rate in realistic 5G environment is about, normally we talk about hundreds of megabits per second. Okay, so that is why basically it could be able to support 4K or 8K video delivery and probably some basic three DOF immersive applications. But definitely we need to move on in order to support more advanced scenarios. Latency. Okay, so probably if you work in the 5G area, basically you can see several years ago people talk about 5G. Okay, we should be able to support end-to-end delay of 1 millisecond, but effectively, probably that's nothing that really achievable. So nowadays, we mainly talk about, for instance, in ultra reliability and low latency applications, we mainly talk about 1 millisecond over-the-air interface. That is much more reasonable. Okay, so, and the other observation is, if you talk about one-way traffic, for instance, video on demand or video streaming, without interactions, the requirement is much, let's say, lower as compared to the interactive applications. And the other, let's say, point I'd like to mention is basically we are not talking about conversational interaction like people using Skype. You may say, okay, what's wrong when I use Skype? So basically we can clearly hear each other's talk. But here we are talking about more mission critical applications. Later I will give some examples here. And also, sometimes latency bottleneck does not really come from the network side. Okay, so again, I will talk about this later on. So now, if we look at the general picture here, there's no doubt in a few years' time, in this world, we will have various 5G islands in different areas, but all of them has to be connected through internet. So now the situation is, when we talk about local network environment, for instance, within a common 5G network, everything works fine. But how can we enable such kind of long-distance communication? Okay, we don't want the future network, I mean the internet, to be the bottleneck that prevents us from doing something really, let's say, fancy with adequately supported user experiences. Talking about latency, so if we look at the careful, what are the, let's say, key contributors to the overall latency? We talk about propagation, queuing and congestion, and also information processing, like security. So people use, let's say, HTTPS, for instance. That naturally will introduce additional processing latency. Okay, and in order to bring down comprehensively the overall latency introduced from different attributes, basically we can have different techniques. Like, for instance, for propagation, you can always localize the content if the content can be localized. Okay, by content prefetching or caching, etc. And then we can have new routing and forwarding. I think Philip introduced a few examples over there, just to bring to minimize, let's say, the risk of having packets being congested within the network, and also information processing. That's an interesting topic. So it is general vision that the future networks will not be only a bit pipe which is just transmit data. It could also process data, but where is the best location to process such kind of data? That's the question. You could do the data processing in the core network or at the edge, or leave this to the terminals. Okay, so that will have a big influence on the overall end-to-end performance. Especially nowadays, we talk about edge computing. Okay, so that enables some intrinsically supported network capabilities to do something. Okay, without getting the user devices, let's say, loaded with this kind of information processing. Okay, so what is the best solution in order to minimize the overall latency introduced from both the communication side and the network and the computing side? So basically, that's the this is the example we'd like to show how important or critical interactive applications is. So basically, we envisage these kind of applications. We can have a distributed music band located from different locations. How to make them how to orchestrate them together, even though they are physically located at different places. So basically, that requires very stringent synchronization between different players at different locations, as well as the audio devices at different places. So we had some, let's say, study mostly during the past few weeks. For instance, nowadays there is a protocol called Dante, okay, which supports the delivery of audio through the Ethernet. Okay, but that's only the Ethernet. So basically, the thing is, if you want to strictly synchronize their music devices at different places, the maximum delay between these devices should be at most 5 milliseconds. That's the upper bound. So ideally, that should be below 3 milliseconds. Okay, so that's another, let's say, very stringent, let's say, requirement from such kind of applications. So basically, as you can see, in the future, you can envisage, okay, so currently we have this kind of, let's say, holoportation, where you can holoport some player to the stage to get interact with the audience. But in the future, why can't this happen? Okay, but basically, as compared to this kind of one-way traffic, one-way application, this kind of interactive applications is much more challenging. Okay, so in addition to this kind of audio synchronization requirement, as you can see, we also have this kind of, for instance, the conductor probably is located in another place. Everyone needs to see the motion of the conductor, and also the other thing is they need to listen to the other part in order to get orchestrated. So even without talking about advanced senses like immersive video, audio synchronization in this case is still enough challenging enough for us for the moment. Okay. And then that brings to the conclusion here. So basically, we can have the vision that some representative application types will become the driving force for future network design. In particular, we look at these kind of immersive X reality, virtual reality, or augmented reality, or mixed reality, whatever they are called, as well as automation applications. I'm not only talking about driverless cars, but it could also be industry 4.0 based applications. So one typical example is the UK's DCMS funded project, which tries to use 5G and beyond technologies to support industry automation. So basically, we have collaboration with Bosch and Mazak to enable remote monitoring and remote sensoring data processing between the factories in Worcestershire in UK and University of Surrey. Okay, and also the other thing is we have the vision that future network design should have a holistic view about networking and distributed computing. Okay, so it's not going to be a simple bit pipe just to enhance the capability of how it can carry packets. And also probably no more parallel design of SG and future network. Okay, so it is pretty funny. When we talk about mobile networks, we start from 1G, 2G, up to 5G. But we don't have such kind of clear generations in future network design. So basically, the two threads develop in parallel. So the thing is, now in 5G, people start to realize, okay, so basically, if we keep doing this, future network and 5G, basically, at the end of the day, people need to use both technologies in parallel to deliver their service across a heterogeneous set of network environments. How to provide this kind of seamless interconnection, at least, to enable such kind of end-to-end service insurance, that will be the key challenge. Yeah, so that's about it. Yeah, thank you.
Thank you. Questions? Can you go to the microphone, please?
Hi, James Crawshaw from Heavy Reading again. You mentioned that there was some sort of dynamic network slicing, which was an evolution of 5G capabilities, which would enable setting up a new network slice in 2 minutes or under 2 minutes.
Yeah.
How does that compare with the current 5G technology that's being deployed, and what's the limiting factor? Why does it take 2 minutes and not 2 seconds, or whatever?
Okay, thank you. So basically, different people may have different, let's say, visions of how network slicing should be enabled. Okay, the simplest version is basically you pre-provision your virtual resources and network functions to form some static slices. But in some cases, like emergency service, so you may have created some on-demand, some, let's say, temporary network slice to support some applications. So this is the main purpose we have in mind why we should do this kind of thing on demand. So the key limitation about that leads to this kind of minute order creation of slices is mainly about software. Okay, so basically, because we talk about a virtualized environment, and then if you want to spin up not only the bandwidth resources, but also virtual CPU, virtual memory, that will cost time. Yeah, so currently what we can best achieve is probably 1.5 minutes. Yeah.
There was a question over here. I'll give you this microphone.
Okay, thank you. Thank you very much. I had a question on the latency synchronization that you mentioned. So I was wondering, do you think it should be done inside the network or outside the network?
Both.
Both,
yeah.
But then if you do both, then there's a need for coordination.
Yes, yeah. The thing is, basically, if this is, I think this is not only about this particular application. So many applications, including the industrial applications, basically you need both the computing and the networking latency to be combined together. So that is why basically it still is a research issue. For instance, for computing latency, you may consider to have this kind of processing on the terminal side or at the network edge, which scenario can save more, let's say, latency. That's the issue. And also, of course, there will be other, let's say, factors like scalability, this kind of complexity, etc. Yeah, but I agree with you. These kind of things cannot be, let's say, separately considered. You need to coordinate.
Okay.
Yeah.
Okay. Thank you.
Okay.
Any more questions? Yeah, I was certainly interested in the what you were saying about orchestras, and as I know that an orchestra needs a conductor if it's more than 25 feet across because of the simply the delays in acoustic sound.
Yeah.
And certainly that's, doing remote performance properly is something that needs attention in the core network as much as anywhere else.
Yeah, so I think probably the max I'm talking about probably in the near future, okay, not in the long term. So basically, one of the key, let's say, target for exploring this kind of applications, we just want to find what is the maximum that we can do. For instance, can we do this, for instance, between Surrey and London? Or even beyond, or even in Scotland, for instance. Okay, yes. So then with more, let's say, emerging technologies, probably we can talk about more large-scale application. But indeed, actually, our starting point is probably from the campus network only. Probably one team is in the west campus and the other in east campus, all connected to a single network, and we can take from there.
Yes, I mean, you should be able to do that with IP.
Yeah.
But when you start going further.
That's another question. Yeah.
Okay. Well, thank you indeed.
Okay.